Why I said this is pretty cool is basically if it is some photographs taken by a person with a decent camera, it is not a great thing, right? Of course, anybody with a good camera can take pictures like this, right? Um, Clear photographs with no loss of detail, etc. But let me tell you the secret. These are not real photos. These are photos generated by an artificial intelligence algorithm, right? So that means these persons don't exist in the world. These are created. These are fake people, right? So that is what makes it cool. No person exists. This boy doesn't exist in the world. This is a generated photo, fake photo. But if I don't tell that, you don't really think that way, right? There is nothing, no detail in the image that makes you suspicious, that make you think this is not a real photograph, right? You may think that these people actually exist. But let me repeat, these are fake photos. These people don't exist in the world, right? So we will see what has created this kind of photographs, how AI has evolved itself to this stage. You know, I hope you see the difficulty in this task, right? So even as humans, we cannot do this job, right? We know how a human looks like, how the human features, that are the face features and the hair and everything that is there on the human body, we know how it naturally is, right? Despite that, it is very difficult for us to actually come up with this kind of a fake output. But the machine, the artificial intelligence, can do that to a greater, surprisingly greater extent, right? I want you to see the value of this particular AI tool, right? So look at the shade on the face, right? So natural. It doesn't look like any doubts are created as if it is a fake, right? So it is as good as a really taken photograph. The directions of the shadow, everything looks like very natural, right? So there are this is the website itself, this person doesn't exist.com. So these are all images generated by artificial intelligence. I'll share these links. You can investigate further, and there are codes also to train these models. If you are interested on your own, you can do that. So this is imagined by a GAN. This is not actually an existing person. This is an imagination of a computer, of an AI algorithm actually. So now this is all done by a GAN, Generative Adversarial Network. Today you are going to uh, know what a GAN is about, right? So I just wanted to show you some of the coolest applications of GAN before we actually discuss the concept. It seems there was a doubt. Let me just check. All right. Yeah, no problem. Let's go. Yeah, so that's something that cool that I wanted to show to you. So before we actually discuss GANs today, let us try to understand the words in it. Generative adversarial networks, right? So the first term is generative. So what do we mean by generative? So in machine learning, typically the models are broadly classified into two models, which is generative models versus discriminative models. So we will see each of them in detail. So the names themselves are pretty informative. When we say generative, what we mean is the model, just one second, I feel something not right with. Sorry about that. Something in the throat was not very comfortable. Yeah, anyway. Right. The names themselves are pretty informative. When we say generative, the model is trying to um, learn or model the distribution of individual classes, or a general data distribution. So when I say data distribution, you can take an example. Uh, Take the example of faces. So imagine the space of human faces, how they look like, different geographical regions, the faces vary, right? Uh, Different age groups also will have variety in data in the faces, right? If there is a probability distribution that is that is spanning on all the faces in the world, that's a probability distribution of faces, human faces, right? So when a machine learning model tries to model the distribution of individual classes, so you can think of uh, probability distribution of digits, right? Digits 1, digits 2, or all the digits also. What it basically means is the image, which is 32 cross 32 pixels or 64 cross 64 pixels, anything like that. So it models all the models means, it represents, basically it represents all the data belonging to a class. It can be faces, it can be apples, it can be data of heart patients, anything like that. So what is the possible data? What is the, let us say you are deciding the heart, whether the patient has a heart disease or not, based on only two inputs. It is very unrealistic. In order to make you understand, I'm giving you this example. Let us say only the BP and the sugar level. Let us say this is not accurate, I know, I'm just bringing an example. The doctor is just looking at only these two data: BP, blood pressure, and sugar, thing about a particular disease, right? So all the combinations of BP and sugar, you think of X1 as BP and X2 as sugar. It has values, right? The sugar may be in around 150, 160, and then BP is similar, 120, 140, 130, like that. So all these possible combinations of X1 comma X2, if you model, if there is a generative model, probability distribution between these two, then it is called a generative model. On the other hand, what is a discriminative model? A machine learning model that learns to discriminate between couple of classes or more than two classes is called a discriminative model. Think of a classifier. For example, in the morning we have seen decision tree. Decision tree, what is the objective? Given an input, it will try to see whether it belongs to class 1 or class 2 or class 3. It is discriminating, right? Particularly I'm talking about the classification tree. So it has to learn the boundaries between the classes. The objective is learning or classifying. That is a discriminative model. So there are some other models in machine learning. What they do is they'll try to understand what makes a realistic data. If I say BP is equal to 1000 and sugar is equal to minus 200, everybody will say, no, that is not a correct data. That is wrong. There is something wrong about the data. We don't generally see BP is equal to some negative value and sugar is equal to some 2000 value or something like that. That means the model will obviously immediately say there is some issue with the data. This kind of data will not occur in real world, right? So that is the objective. The generative model will understand the data, and using that, what we can find out is this data realistic? Is this data more common? Is this uncommon? What is the probability for this data to occur, right? For example, think of all the heights. The Indian population, typically the average height of Indian population is, let's say, from 5 to 6 feet or 6.5 feet. So most of 99% of the Indian population, the height of Indian population will be between 5 feet and, but tomorrow I give 9.2, 9 feet 2 inches. The model will say this is very unlikely. I don't think general Indian will have this much height. So generative model is trained to understand the model, and when we input some input data, it will say whether it is a common data or it is unlikely data, it is rare data, it is almost impossible data. So such information is captured by generative model. Okay, so that is the difference between discriminative model and generative model. Right, I hope things are clear, but stop me. I'll try to explain, because this is very fundamental to the slides that we are following, that they follow later. right? So generally we have not, generally, in typical machine learning introduction courses, generative models are not discussed because they are little advanced. Most of our applications are about discriminating, right? Whether the input belongs to class 1, class 2, class 3, or if given an input, what is my output, right? Probability or f of y, f of x. So given x, I have to predict f of x. So that is more discriminative machine learning. So generative machine learning is, as I said, it understands the data. It will tell, given an input sample, whether it is common or it doesn't make sense, things like that. All right. So let us take a simple example to understand what a generative model looks like and how it does what it does. So let us say this is data, one-dimensional data. So as I said, this can be height in feet, right? X-axis is the height in feet. So there are some population who are in this height range and some other population who are in this range. You can think of, one is male, one is female. You can think any other way also, but I'm just giving an example. So there are two categories roughly, right? So generative model, as I said, is interested in how the input feature and the label Y occur together, right? So let us say the label in this example is male and female. Two categories are there. Let us say this is male because typically they are a little taller. Female, the green class is female. Two labels, Y is equal to male or female. And input X is basically the height in feet you can think of. So generative model is interested in how input and output occur together. So tomorrow, if I say one green dot, if I say here, that means I found a girl whose height is 9 feet. Then obviously the model thinks like this is unlikely. Whatever data the model has seen, it has seen only these heights in female. But if some sample occurs here with green color, it will have very, very like close to zero probability. The model thinks that it is a very rare case. I am giving you only 0.00001 probability. But if some sample falls here, it will say, yes, it is likely. 5 feet 4 inches or 5 feet 6 inches is a common height for females in India. So because my training data also says that model has seen some data in this region, so it will have a better probability. The model is happy. It doesn't contradict the observation, right? So generative model tries to find such relation, the probability of X and Y occurring together. It is called joint probability. For example, the label green, and then X is equal to 5 feet 4 inches, right? So what is the probability? Because there are a lot of samples in the training data here, the model will assign great probability, high probability for those X comma Y, because a large population of Indian female has height of 5 feet 4 inches or 5 feet 5 inches, things like that. So that is what called joint probability. Probability of X is equal to something and Y is equal to something happening simultaneously, right? Using the probability basics, we can write it as probability of Y times probability of X given Y. So joint probability can be divided into the prior on Y and the likelihood on X. So these term, probability of Y is called prior. What is the probability for the female? The probability for being the person to be female, and then given it is a female, what is the probability for height 5 feet 4 inches? Whatever, I'm just giving some number. So that is how the joint probability can be divided, right? Let's see, there is a question maybe. Oh no, not a question. All right. So generative model uses the joint probability distribution to determine the label of the example. How? Let us see. So these are two classes, as I said. One is green class and other is yellow class. So the green class is modeled by one distribution and the other class is modeled by another distribution. Let us say for simplicity, I'm choosing the simple Gaussian distribution to model probability of X given Y. So given Y means, I know this is a green class. That is why given information Y is equal to green. So what is the distribution of X? Here, I know I'm considering only the male category. y is equal to male, then what is the probability of x? So let us say 5 feet 7 inches is common. So this will be centered around, the Gaussian will be centered around 5 feet 7 inches. And to the left and right of it, there will be some mass, because some people will be slightly taller than 5 feet 7, and shorter, slightly shorter than 5 feet 7 also. So mostly around that mean value, you will see strong mass, strong probability, right? So this is how the generative model generally models. So if you know any other information, any more domain knowledge about these heights, you can use better modeling strategies. But generally what we do is, because of the simplicity, we choose Gaussian model. And the name itself is normal distribution, right? The Gaussian distribution is also called normal distribution because most of the physical phenomenon in the real world follows that normal distribution. It is normal to, as a natural choice, the physical phenomenon sometimes, I'm not saying everything, but it is not a bad assumption, assume these things follow a normal distribution, right? This is how they look like. Probability of x given y. When y is equal to green, it looks like this. When y is equal to yellow, it looks like this, right? We can model these things given the data. I can, for example, I have 2000 training data, right? So I can compute the mean height and assign the mean of the Gaussian to this. And similarly, for male also, I can compute the mean height and give the mu of this normal distribution. Similarly, I can compute the sample variance, right? So the Gaussian is specified by two values. One is mean, another is variance. So whatever training data I have, I can use to compute mu and sigma. That way, I have probability of x given y here and here. From the training data itself, we can find out this distribution. So this distribution generally, as I told you, is referred to as likelihood. Likelihood means how likely is this x value, or how rare this x value is, right? As I was saying, given 5 feet 4 inches, it looks very common, right? So value of x is high. As I said, a girl with 9 feet height is very rare, right? That likelihood of x is equal to 9 given y is equal to green is very, very, very small, almost zero, right? So that is what likelihood means. Whenever you hear the word likelihood, it means the probability for that value to occur, right? That is what likelihood is. And it can be defined for each class separately. This is what we are doing here. When y is equal to green, there is a different distribution. And when y is equal to yellow, there is a different distribution, because these two classes are different. The heights observed in this class and this class are like almost they're also, although they're similar, but they're, that is why we are modeling it differently. All right. So how do we use the generative model to infer? Let us say I found a height, which is this value. So x-axis, as I told, is the height, right? So tomorrow there is some 5 feet 4 inches or 5 inches, some height is there. So I'll see where it fall. So what is the probability for this to be green? What is the probability for this to be yellow? It looks like this is probability for the probability for green is higher, right? This is the probability for green. So let us say, imagine a y-axis standing, it is maybe around 0.1 or 0.05, things like that. But what about the probability for yellow class? It is already zero here. When you interpolate this curve here, it is close to zero, right? It will not go below zero because the probability value is always greater than or equal to zero. So that means the probability for this x value in the yellow class is zero, almost not happening. This class never sees this height value. So in that case, it is easy to assign green label for this class, because yellow, the probability for this to be yellow class is almost zero, but here it is non-zero. So this is the value, whatever is this height, that is the probability for this sample to belong to green class. So this way, generative model can be used for classifying also. Whatever class has the likelihood, better likelihood, you assign that class, right? On the other hand, generative model also tells you more about the data, right? So whether this kind of data is meaningful, not meaningful, is it rare, is it common, things like that. All that is captured by a generative model, right? So this is another example. Let us say you want to find out based on the speech, right? The audio output, you want to see the person is whether a man or a woman, right? Generally, the woman's pitch of the speech will be higher. Voice pitch of women is higher than the men. So that is why the pink samples are women and the green samples are men. The pitch value for men is typically smaller and women is typically higher. That is why these data is more towards the right side of the x-axis. So this is how I can model. Similarly, whatever example we have seen, right? Similarly, I'm estimating my mu and sigma. So this is how my women class is standing. And similarly, my men class is standing here with slightly is here and this mu is here. Now, so how do I decide how to classify? I will see where those two are intersecting, right? So this is the threshold. This is the point at which these two distributions are intersecting. And to the right of this, the probability for women is high. That is why the pink graph is above the blue graph, right? So everything, all the samples towards this side, I can assign the category of women. Although there will be some outlier men whose pitch value will be higher than typical men. So those will be misclassified. That will be error in classification. Similarly, if the pitch value is less than this particular threshold, because the probability for men class is higher, see, this is the probability for women class and this is the probability for men class, if the x value is below this one. So all the samples below this threshold will be classified as the men class. Again, there will be some outlier women samples whose pitch value is lesser. So those will be misclassified. So there won't be 100% accuracy, but it is quite a good modeling if the classes are separable, right? So this is a generative model. All right. So the gist of generative model is basically we are thinking of a model that is generating random samples from the distribution. So you have to think as if this model is generating all the possible women pitches, and this model, the blue one, is generating all the possible men voice pitches. That is why it is kind of modeling, right? It understood how men's pitch look like, and this also understood how a woman's pitch look like. So that is how they generate woman voice and men voice. You have to think that way. So all right, so what about the discriminative model? So discriminative model, on the other hand, the focus is not on generating data. The focus is on how to distinguish different classes. Given an input, how do I learn the boundary? How do I classify, right? Although generative models are also doing classification, it is only a byproduct. The focus was more on modeling the data, understanding what is normal, what is not normal, by giving a probability over the input space. But of course, we can do the classification also as a byproduct. But discriminative model, right away, we want to classify. We don't care how the data is modeled, how the data is occurring, whether the model, whether the data is realistic or not, we don't care. All that we care in the discriminative modeling is how to distinguish different classes. The goal is to find the decision boundary. Classification is the goal in the discriminative models. Yeah, as I said, they do not care about the distribution, right? All that they care about is the classification error. They want to minimize the classification error. That's it. So in the same example, what they do is, so they'll assign label 1 to this class, green class, label 0 to the yellow class. Now they'll simply have a threshold. Nothing, there is no modeling, there is no Gaussian, nothing. All that they focus is how can I draw a threshold which classifies class 1 against class 2, right? And the probability distribution they model is posterior, probability y given x. What it means is, given x, what is the probability for y is equal to green? What is the probability for y is equal to yellow, right? So that is what they worry about. They try to model only probability of y given x. Yeah, so whatever class that has better or higher probability of y given x, it will be assigned to the class. All right. So just try to compare the generative model. What we did is, what was the probability of X given Y, right? So this is probability of X given Y. Whatever class has probability of X given Y more, we assigned in the generative model. But in the discriminative model, we'll go for probability of Y given X. Given input, what is the probability for Y to be green, or what is the probability for Y to be yellow? Whichever is more, you will assign that, right? All right. So this is another example. So the what is, we are trying to find out the boundary based on the number of mistakes. As I said, the goal in the discriminative model is to minimize the classification error. Number of mistakes have to be minimized. So I'll start drawing my threshold here. If I draw a threshold on the right is women and everything on the left is men, almost all the samples are classified as women. That is why number of mistakes is high at this point. Let us say if I draw a line here, there is one mistake which is now correct, because on the left I said men, on the right I said women, right? So one man getting rightly classified. So there is one drop in the number of mistakes. So if I just go on moving towards the right, number of mistakes is reducing, continuously reducing. So the moment I reach here, so this is the minimum classification error I can get. If I draw a boundary here and say everything on my left is the men class and everything on the right is women class, there are only 1, 2 mistakes, right? So this is the smallest number of classification mistakes if I draw here. Again, if I go towards the right, there is one woman getting misclassified. And again, I come here, one man is getting rightly classified. Previously, this was classified wrongly as woman. Now, if I move here, this is getting classified correctly. So this is the minimal error. I cannot minimize the error beyond this point. So I can go draw a line here or draw a line here and say everything on the right is my women class and on the left is men class. So this is how a discriminative model works. To always find the boundary. The goal is to classify correctly, as much correctly as possible, to minimize the mistakes is the goal here. All right, so these are broad categorization of machine learning models into generative model and discriminative model. So again, this is a never-ending problem. When to use what? So which is better? When to use what? Which is better? These are, very important questions. Whenever we learn a model, we need to understand what is the advantage, what is the disadvantage, when I can use this model, what information I need to ensure so that this will be very useful, and what situations I cannot use this model. So all that information is very crucial in machine learning. Okay, let us understand what is the advantage of generative model and what is the advantage of discriminative model. So generative model, there is less chance of overfitting because you are not worried about minimizing the classification, right? If you are worrying about the classification minimization, you will overfit on the training data. But here, generative model is worried about uh, understanding the data. So it will accommodate the outliers also because it is more careful about understanding the data. But on the other hand, discriminative model is worried about only classification accuracy. It has some training data. It has to minimize the error, classification error. Because of that difference in focus, generative model is less prone to overfitting. So as I said, if this is class 1 and this is class 2, if I model it as a Gaussian, these two samples will also fit in the red Gaussian. And this blue, despite having an overlap, can be captured by another Gaussian of the blue class. So during the test, all my white dots are test samples, right? My test data, if I try to see, they are falling here, right? Because my red Gaussian explains them better, probability of X given Y is equal to red will be more for these white samples, right? Remember, generative is probability of X given Y. So given I am looking for red class, Y is equal to red, what is the probability for white? It is more because it is clear Gaussian, red Gaussian. If you look at the blue Gaussian will be spreading in this area, right? That is why the probability for red class, and it is right also. That is how the generative model classifies them into red. On the other hand, if I try to learn a discriminative model, which is a simple linear classifier, I'll try to learn. So the line says everything on my left is Uh, because during the training, it misclassified only 2 samples. That is the minimum possible error. That is why the model, discriminative model, is happy to draw a line here and say on the right is red class, on the left is blue class. But look at the test data. All the test data is misclassified, 100% error, because the focus was different, right? So this is the case where generative model should be preferred, right? So the overfitting is minimal compared to the discriminative model. But at the same time, some issues with the generative model are like this. Outliers affect the model performance very badly. As I said in the example, there may be some actual samples. Some let us say some girls are there who are taller, 7 feet or 8 feet. So, so these are the outliers. They are possible, but very, 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 very rare, right? I heard a doubt. Maybe let's just see. Okay, it's not a doubt. Okay, sorry about that. Yeah. So when there are outliers in the data, because we are modeling using a Gaussian, the mean computation also need to consider these two, right? These two will drag the mean from actual mean to be towards the right, right? Because if you don't consider these two, the mean will be somewhere around here, right? But if you consider these two also, the mean will be moved towards right. And similarly, these yellow samples, they they are outliers. They are lying very, very far from the majority of the yellow classes. So if your data has these outliers, the generative models will be erroneous. So this is how the mean will be destroyed, right? Only to accommodate these two outlier samples, sometimes they may be wrong also, right? When the data is being collected, there may be some errors, data acquisition errors, right? So because of those mistakes also, the estimated parameters mu and sigma may be erroneously estimated. So because of that, everything looks very messed up. So if there are outliers, generative model is not a good idea, right? We have to remove those outliers and then estimate the parameters. So we need to do data pre-processing. So now if you see, this is the test sample, white sample. So if I don't have this green and yellow Gaussians, you will obviously say with more probability this belongs to yellow class, correct? Because more yellow samples are nearer to that white sample than the green sample. But because of the outliers, the estimated probabilities are more for green. See, this is the probability for green class at this X. And only this much is the probability for yellow, which is smaller than that of the green. That is why if you follow generative model, this will be labeled as green class. Although it is very far from the majority of the green and it is very close to the yellow, you are doing a mistake because of these outliers. Here also, these yellow outliers, otherwise you will see a Gaussian here only here. Because these two are there, they're dragging the mean towards them. Yeah, so that is the case when you have to carefully apply the generative model, right? Also, generative models need a lot of data because the mu and sigma will be meaningful when you collect it from a large sample. If you just have only small number of samples, these estimations may be wrong, maybe not very accurate. So that needs a lot of data. But on the other hand, discriminative models can work well with less data also. So classifiers, for example, as I was saying in the morning also, the classification trees and all, they may be okay with not having more data. Definitely more data is helpful, but in case it is not available, so some of these discriminative models are good. And also generative models need relatively more computation. So in order to estimate the parameters and all that, you need more computation than the discriminative model. So this is how they compare generative versus discriminative. So the goal in discriminative modeling is probability estimates. We want to understand which data is more likely, which data is less likely. When the probability for data is more, when the probability for data is less. On the other hand, discriminative model, the goal is to classify. Classification rule, they are all focused about classifying with minimal training error. Also, the performance measure, as I said, is likelihood. What is the probability of X given Y? Given Y is equal to green class, how does the probability for X vary? How likely each X is? So that is what the performance measure is. Here, discriminative model says, what is my classification error? How much is my misclassification rate? So that is what they are worried about. And again, generative models are more vulnerable to outliers. If you have outliers, your mu sigma will be um, erroneous, and because of that, your predictions may also get erroneous. So discriminative model, you may succumb to some misclassifications. When you are modeling, the data itself is complex, and you may end up misclassifying some of them. All right. So this is broadly about discriminative and generative. Yeah. So these are some more data, some more notes, how to, differentiate and what are the um, aspects, characteristics of both the generative model and discriminative model. All right. So everything is fine. Generative model and discriminative model, we understood. So what is the focus in generative? What is the focus in discriminative models? And all that we have seen. We have seen a couple of examples also. So we have modeled using the training data. We have modeled, and by an assuming normal distribution, we have modeled a generative model. And the discriminative model, for example, in the morning we have seen trees, right? So that is one discriminative model. And linear regression, logistic regression, all those things are discriminative models only. So why do we need generative model? So discriminative model, it is clear. I want to classify, I need a discriminative model. I need to predict Y from X, I need a discriminative model. But when do we need generative model? So there is something called density estimation. As I was saying, for example, so we want to understand about the data. For example, take the same example of Indian population, right? So the government may wants to understand about the population. What is the age groups? What is the health properties? What is the general weight distribution, height distribution, all those things, right? So density estimation is one of the primary applications. It wants to understand what age group is more probable in India, right? What is the weight range that is predominantly or majority of the people are occurring in which weight range, things like that, right? So this is more about the data. It is nothing about classifying or being discriminative in class wise, but it is more like the data is being understood on a broad level. So that is called density estimation. It has to understand, for example, if you are modeling the data, the distribution of the data using normal distribution, you need to find out the mu and sigma, right? So that estimation of parameters is called density estimation, right? So as I said, based on the application, the mu, sigma, or any other complex modeling has to be followed. All right. So another application is sample generation. So what it means is, let us say these are training data. So now I'm talking about the image data. So I'm talking about the color images, RGB images. So if I want to generate more data, for example, if I have the distribution, think of this as a box which generates this data. So think of it as a magic box from which the data is coming out one by one. So I don't know generated. Let us say if I can come up with an algorithm, I show these training examples, and now I'll tell the algorithm, see, these are my training examples. I'll give you 1 million images. What I want you to do is come up with some magic. Whenever I ask you to give me images, you should be able to give me images. As if, sampling data from that distribution, right? So this is called sample generation. Actually, in order to generate a photograph, you have to go into the real world with a camera and take photos. That is how we generate the model, we generate the data, right? But I want a magic. I want an AI algorithm to do that. Artificial intelligence algorithm to create data for me, to create samples for me. So what I'll do is, the GAN is exactly what it is doing, right? GAN is one example for a generative model that generates samples. We will see more detail how it happens, but I want to let you know the applications of generative modeling. So this is one, which is density estimation, and second one is sample generation. Why do we need? There are a lot of applications. So going into the real world and taking photographs may be easy because all of us is having camera phone. Nowadays it may be easy, but think of cases where data is very scarce. Data is very difficult to generate. For example, if you are taking about if you're taking data about the space, right? It is very costly to take photographs of space, and also underwater imaging and um, medical data, right? Sometimes it is difficult because taking medical photographs, which are x-rays, mris, all these things, these are very not healthy also. If you are a patient, yes, it is, there is no other way. The doctor has to find out what is there inside, so he or she will subject you to x-rays and other mris, things like that. So, but for data collection, we cannot ask people to undergo scannings, etc., etc. It is very dangerous if you expose yourself to more such scannings, etc. So these applications require a generative model which will give us more data, right? If I want to learn a classifier or any discriminative model on that data, I need data. Without data, I cannot learn significantly. So that is where we need a generative model which can give us data, right? So there are a lot of such applications where we don't have enough data. We want generative model to create data for us. So that is where generative modeling has a lot of applications. So GAN is exactly fitting into this application where we don't want to actually, take the real, create the real data, but instead we want a machine to do a very good job of creating data. So if you now connect to the photographs I have shown to you in the beginning of the presentation. So those are, if I don't tell you, there is no suspicion for any of you, I'm pretty sure. But think of the quality and the realistic, um, the belief it has created, right? So that is the topic of today's presentation. So we are going to talk about generative adversarial network, which is one of the generative models. All right. So I tried to tell you why we study generative modeling, but anyway, let me just summarize. So we have to, so because images are very high dimensional data, right? So most of us are carrying handphones that are at least 8 megapixel, 10 megapixel. It's a very high quality images we are taking today, right? So we are in such a big, like high dimensional data. I was giving very simple examples. One dimension example, height. Height is only one number, right? Modeling the height, distribution over height is very like the toy example. But now think of creating data in very high dimensions. High quality images means you are in thousands and millions of dimensional data, right? So obviously it is very difficult. We can't even imagine such high dimensional data. Now we are thinking about creating data in those dimensions, right? So that is where we need generative models. And we can simulate possible world scenarios for reinforcement learning. So I told you, right, there are some scenarios where it is very difficult to create real data. To generate real data, it is very difficult. For example, think of a robot playing in a chess or playing in a Go, some game, some board game. It has to train itself by playing thousands and thousands of games. As humans, we are not jobless to train the model by actually playing, right? We can't spend 1,000 hours playing with a computer to train it, right? It needs a lot of training. Obviously, it is machine learning. It needs a lot of training, and we can't employ humans to play chess against it, right? So what we do, we simulate. We simulate such environments. Not only in the chess example, but think of playing other games, Atari games, or these days kids are playing all these shooting games and all, right? So every game, all the computers, they need a lot of training. right? So we simulate all those environment so that the computer plays against those things and improves its playing skills, etc., etc. So RL is one of the major area where it requires synthetic data. We need a lot of synthetic data. Also, think of driverless cars. So we need to test driverless cars in as much thoroughness as possible. But we can't put that on the real road, right? Because if it hits the real people, they will die. It's really dangerous to actually test in the real data. But we can simulate real world environment without any damage. Even if it commits a mistake, there is no people who are getting accidents, right? So all such applications require real looking data but synthetic data. So that is where we need GANs. We need generative models to generate data. I heard a chat message. Let me see if it is a doubt. No. The question is about, is GANs only for image applications? No. I will show some GANs that played music. So GANs are there learning speech. They're writing songs, right? So as they show in all these science fiction movies, robots are doing creative stuff. They are painting, they are composing music, they are writing poetry. Yes, I'm not exaggerating. There are a lot of applications, demos also. I have some today. I'll show you the music played by them and the paintings drawn by them. I'll show. Yes, there is no limit. That's why it is exciting. This is there. AI is already there, right? I've been using Alexa for some time now. It understands me. It not only the typical tasks. See, reading my calendar, finding out my schedule. These are very simple things. Now, any other graduate student can write a program to do that. But this is AI at different level, right? So understanding the data, right? For example, the data of flex. Think of the variety. Every country has different face features, and not only that, and understanding the real world. For example, one of the photos has a sunlight on the face, and depending upon the sunlight, there is only one pattern of shade that can happen, right? So that's what I'm talking about. Such realistic looking data, right? So a lot of applications missing data in semi-supervised learning. So when the data is missing, for example, see in experiments like Large Hadron Collider, LHC is there, right? So in Switzerland, you might have heard of this place, LHC, where they try to collide the subatomic particles, electrons, protons, things like that, because they want to understand the modern physics, like atomic physics, etc. It's running experiments. Imagine losing some data. There is some missing data. Somehow the data is not recorded. They can't conduct again. It is costly, it is time taking. Some scientists may even die during the experiment. Things like that require, I'm just giving an extreme example so that you will understand. But it is not the only example where the missing data has to be somehow manipulated instead of conducting the experiment again, right? So that is where we need generating portions can be simulated as much close to the reality as possible. So there's a lot of such generative model applications available where we need to train generative models. All right, so we understood now that there are a lot of scope for generative models. How do generative models work? All right, so as I told you, maximum likelihood, maximizing the likelihood is the principle. For example, these are my samples. What it means is, okay, this is where my data is occurring majority of the, so majority of the data is occurring here. That means the probability for these X values is high. Similarly, these values are there. So these values is also high. So from the given training data, the model tries to maximize the probability wherever the training data is there. Right? This is the principle. I'm not going into the technical details. So if you see the model parameters mu sigma are chosen or found out such that the log probability of X is maximized. So basically it's probability, log probability, because it has some computational advantages. in log product becomes sum, etc. That is why logarithm of mn is equal to log m plus log n, right? So that way the probabilities which are small quantities will be sum instead of multiplying. If you multiply less than one quantities, the product will be even smaller. So additional facility we use log, but basically what we are trying to do is probability of the data is maximized wherever the training data is there. That is why I said a 9 feet girl is very unlikely. The probability to find a 9 feet girl in India is very, very less. But on the other hand, 5 feet 4 inches and all is high. Wherever such data is there, you have the probability for that data higher. So that is how you train the parameters theta to have higher probability for data observed and lesser probability for data not observed. That means that data is not realistic, right? So yeah, just understand that maximum likelihood is the way to train generative models. Okay, broad categorization of generative models. There are two broad categories: explicit density and implicit density. So for example, when I model this density as a Gaussian with mu and sigma, that means I am taking explicit density. Explicitly, I am saying my density looks like a Gaussian distribution with a mu and sigma. But if I don't assume anything like that, I simply say it is a black box. It does only sample generation. I don't want to restrict to Gaussian or any other distribution. I'll simply say there is some distribution which I don't know. It is just generating samples one by one. So that is called implicit density. So what we have discussed by modeling it as a Gaussian and estimating the mean and variance from the training data, that is called implicit density estimation, which is one way to achieve maximum likelihood. So today, GANs exactly fall in this implicit density. They don't assume any density, shape. They'll simply treat it as a black box. Okay. Now let's see what they do exactly and how they train to do some wonderful creation. So this is introduced by a PhD student, Ian Goodfellow, in 2014. So this fellow is a great inspiration actually. So this is not very late. This is only 2014, invented in 2014, when I started my PhD in IISc Bengaluru. So not only me, a lot of PhD students got inspired from this fellow. Yeah, he was a PhD student, and guess what? He invented these GANs when he was in a bar in Montreal, Canada. So he was studying PhD there, and yeah, so he might have gone out with his friends to a bar, and during that period, he got this idea, and it is considered, it is believed to be the coolest idea in machine learning in the last 20 years. So that means I'm telling you, such a great technique it is, such a wonderful tool, such a valuable contribution to machine learning. So Jan Lucan is the, so if you remember recently, the Nobel Prize equivalent of computer science is ACM award, Turing Award, right? When a computer scientist gets Turing Award, it is equivalent. So Jan Lucan is one of these three fellows who recently awarded, who got the Turing Award for 2019, I think, yeah. 2019 he was awarded. So he's a great scientist, computer scientist. He's working in machine learning, deep learning, AI area. He's working with Facebook actually now, Facebook artificial intelligence research. So he said, after knowing about the GAN, he said it is the coolest idea in machine learning in the last 20. Now let's see what it is. Enough of good things about GAN. Let us dive into the GAN and see what it is. Right. So this is basically a neural network. The name itself says generative adversarial network. So network is for neural network, and the generative adversarial, there is a generator which generates the data, which is for creating the data. That is what the generation is for. So discriminator, we will see what it. Discriminator, as I said, discriminative models is the idea is to classify, separate the data into classes. So here, this data, this discriminator classifies into real and fake. Yeah, I was trying to see. Yeah, just give me a second. Right. So discriminator's job is to classify between real and fake. Generator is generating the data. From random noise, it will generate the data. So, so discriminator, as I said, it is a neural network which is differentiable function, and then dfx tries to be near to 1 when the input is natural data, original data. So it is classifying the data to be real with probability 1, right? So as I said, this is a neural network which accepts an image and gives a probability between 0 and 1. Probability 1 means input is real, probability 0 means input is fake, created image. So that is um, the discriminator D. At the same side, the discriminator, when the fake image is fed, it will give probability 0, right? So fake images is generated by the generator. So if you see, I'm going back. So this is giving the generator generated images, fake images. So how does it generate? It will take a random noise and it will convert the noise into, via deconvolutional layers. It will give a input image. So it will create fake image. So when that data, you see this one, it is not very no blurring is there, it is very sharp. But on the other hand, if you see the right side, this is very blurry, not clear. D, it will give close to 0 probability. That means it is not real. The probability for this to be real is 0. Sorry. Yeah, so this is the objective of generator and discriminator. One has to create data, another has to classify whether it is real or fake. So as I said, the role is to inspect a sample if the input is real or fake. Discriminator is the key here. I would not say that is the key. It is also the key because it has to help the generator to improve its performance, right? The generator has to fool the discriminator by creating a fake sample, and the fake is so real that discriminator thinks it is a real, right? So that is the objective. The generator here has to create such a realistic data so that discriminator is fooled. It believes as if it is a real data. So until then, the generator improves itself. Starting in the beginning, it will give something like this. But the discriminator is intelligent. It will say, no, this is not a real looking data. And improves its performance and gives better fake images. So when the generator is really good at creating fake images, then the discriminator will be fooled. At that point, we'll say the GAN is ready to deploy, right? All right. So that is what the roles of generator and the discriminator are. So to make you clearly understand, so think of generator as a fake painter. So this guy is a thief. Or what to do is he tries to create fake photographs, fake paintings, fake paintings, and try to sell to the community. So he is cheating. So what he does is he tries to say this is a painting made by Raja Ravi Verma or somebody else, and clearly the police, who is a discriminator, will see no, this is no way close to a real painting by Raja Ravi Verma. You are a cheat. So obviously this guy gets caught. So because the police is clearly able to see whether it is real or fake, this guy goes back and comes up with a little better. Because see, look at this is absolutely not meaningful, but now this is a little better, and still the police can't be fooled. He say no, this is not a real photo, a real painting, he'll say. And then the generator, this guy, has to improve further. It has to evolve, right? This guy improves his skills. He will try to learn, how to make real fake paintings and all. So again, this guy says no, this is not a real painting, close to the real painting, right? So again, the thief goes and tries to make little more improvements, and then this is also not good enough. That this is still a fake painting, he doesn't buy it. And then the generator again, the counterfeiter has to again improve his skills and tries to come up with this kind of a picture. This is when the discriminator gets fooled, right? This guy thinks it is a real painting, but actually it is a fake painting. The generator is so skilled at generating fake painting that is very close to the real painting. So this is how we should understand a generator and a discriminator. Sorry. Yeah. So the generator continuously improves his skills. Look at the generator images, absolutely noise and some patterns. And slowly, after a lot of training from the discriminator, the generator is able to come up with some meaningful fake images so that the discriminator gets fooled. So this is how the generator adversarial network GAN gets trained. There is one network which is generator. There is another network, discriminator. The role of the first network is to create data, and the role of the second network is to um, classify, identify whether it is real image or fake image, right? Because of the signal from the discriminator, the generator improves its skills, because the only objective of generator is to fool the discriminator. In order to fool, closely looking fake data, right? So that is that is what GAN is about. The training GAN starts from randomly initialized generator and discriminator, and slowly things will be improved. During the training process, generator improves the skills for generating data, discriminator improves the skill for discriminating the data, right? So this is how a generator works. It takes a random sample, let us say 1 cross 100, 1 cross 50, something like that, a random noise it will take from a Gaussian distribution, and then slowly via deconvolution layers, it will be reshaped into two-dimensional matrix, and then it will be padded, and more data will be created in order to look like an image, W cross H cross 3. Because it is RGB image, you will have 3 planes, and width and height will be there because it's a bigger image. So slowly from random noise, it will start generating data. Because of these parameters, the more and more details will be added during the training as it gains more and more information about the data. So how does the generator learn? Because you have training data also. I'll show how the training data is used. Broad overview of generator. From vector, it will learn to create the data. The discriminator, it takes the generated data as input and say cross mark means this is not the real data, right? Because it is clearly fake data, it will say no, this is not a real data, right? If a clean data is passed here, it will say yes, a tick mark will be there, because it is trained to recognize the fake from the real, right? So if you see, this is only a binary classification. Discriminator is doing only a binary classification into real and fake, right? It will output a probability between 0 and 1. If it is towards 1, what it means is the input is real data. If it is towards 0, the input is a fake data. So this is a simple neural network doing binary classification. Sure, yeah, please. Please go ahead. Okay, I haven't seen. I'm really sorry. Right, can we use GAN for supervised and unsupervised models? Right, so yes, we can use. Supervised means there is some label associated with the data, and so only data is available. Yes, it is perfectly used in both supervised and unsupervised. I will show you examples where it is used in supervised also and unsupervised also. Whatever we are discussing now is unsupervised because there is no label. All that we are talking about is only data, creating data, right? So we kept the labels aside in this particular analysis, right? Yeah, I'll come to that. I'll show you where we can use it in a supervisor sense, right? How do we actually train the GAN? So this is how we train the GAN. So this is the generator neural network. It will take random noise and try to generate a generator sample. And on the other side, you have the training data, real data, which is we take a camera and take the photographs in the real world. This is the training data. So you take data from here and present it to the discriminator. Because it is real data, it has to classify it as real. And because this is generated data, let me highlight that. So whatever is coming from the generator network, it is fake data. So it has to classify this data as fake and this data as real. So that way, discriminator will understand how a real data looks like, because you are providing training data and saying there is label for this. The label is only real or fake. Actually, there may be dogs, cats, the laptop photographs, anything, but the label is not their category. We are not saying it is a dog image. We are not saying it is a cat image, nothing. We are simply saying it's a real image, right? So that is how it will try to understand how a real image looks like, how smooth the real images will be, how the background or the greenery, how the sky always looks on the top portions of the image, and on the other side, grass always looks on the bottom side of the image, right? Unless you are taking upside down, but it is very rare. 99% of the times grass will be on the downside and the sky will be on the top side. And similarly, most often the object of interest will be in the middle, right? When we take a photograph, whatever is the focus will be set in the center of the photograph, right? So it will understand, by looking at these actual training data, it will understand how real image looks like. As I said, what occurs mostly on what area, all those things during the training, it will understand. This understanding will be transferred to generator also, because the generator always tries to fool the discriminator, right? This guy is intelligent. He knows how a real data looks like. That is why when the generator tries to fool, it will also learn how the training data looks like, how the real data looks like, because all the generator wants to do is fool the discriminator. So as I showed the example, starting from the random noise, it will slowly improve by adding more details about the data. And towards the ending, it will try to give very close data as the original data. So this is how a GAN is trained, right? I hope it's clear. So you have the training data whose label is real, and you have the GAN generating the data one by one whose label is fake. So initially the discriminator is good because the training data, it will understand and try to classify these samples as fake. But the generator wants to improve. It wants to fool the discriminator. How to do that? By generating better images. By adding more and more realistic data, it will try to improve its skills of generating data, and slowly it will fool the discriminator. All right. So as I said, generator network from random noise Z to sample X, it will convert. So I'll show you how exactly it happens. So this is how it happens. So this is a 100-dimensional noise vector. Slowly, the neural network transforms it into 2-dimensional array, and slowly it reduces the depth. You see, this was the depth, and slowly it is reducing, and the parameters are chosen that way to become 64 cross 64 cross 3 channels. So this is called a DC GAN. This is a very important paper in GAN literature. Yeah, deconvolutional. Generative adversarial network. What is DC? It uses deconvolutions because it is trying to increase the spatial extension from 1 dimensions. It is going into 2 dimensions, right? That is why. So deconv layers are used. All right, so let me just get back. So the generator network, what it does is, from the random noise, it will try to give the input image. So this research has started with images. That is why most of the terminology is associated with images, but it is also used in other areas. As I said, they are creating speech, music, etc. Right? So that means you can think of X not only as image, but also speech, right? Based on the application, you have to understand. But because we are discussing about images, I've shown an example where X is a 2-dimensional output. All right, Z is called latent vector, from which you are transforming into the data sample. All right. Training means you can use any neural network training procedure like stochastic gradient descent, using 2 mini batches, one with the training, actual training real data, another with the generated examples. As I shown here, one is here real images and another is the generated images. For this is fake. So it has to identify which are real and which are fake. But the generator, it has to improve itself to create these fake images as real as possible so that the discriminator will be unsure. It will assign 0.5 probability. That means it is not very sure whether it is fake or real. So that is the
Excuse me, sir.
yes, please.
Sir, how the generator can understand this discriminator images like that? How it know?
So we are giving the label. So the label for real is 1, right? Because we have training data, the data this data will have label 1, right? So this data which is coming from the generator, we label them as 0, right? So now you have data belonging to 2 classes, class 1 and class 0. Now you can train the classifier to do the binary classification. So that is how this network is trained, right? So every time you take the real data and assign label 1 and you create fake data using generator. It can be noise. It can be initially, because this is not trained, it will look like the random noise, right? It will, I have shown this random noise, right? It will look like this initially because it has not trained, right? So all those images will be labeled as 0. Now you have binary classification, label 1 and label 0. So you train this, some iterations. And while training this, the generator also needs to be trained, right? The generator objective is to increase the probability for these, right? The ground truth says 0, but it wants to create the impression that these are real images.
How it can improve, sir? How it can improve the accuracy?
Right. So the neural network, it is like, how does a neural network train to classify dogs? Because it will adjust its weights. The weights that are there in the neural network will be adjusted using backpropagation. And slowly from accuracy 0, it will learn 10, 20, 30, 40, 50. It will learn, right? Via changing the weights. Backpropagation algorithm is there where the loss will be minimized. The gradients will be backpropagated so that the neural network learning happens. So I'm not sure if neural network training is covered. In earlier phases, it is covered. I think I myself have covered neural network backpropagation. So to answer your question, basically neural network training requires data and labels, right? Because you have data and labels, you can compute the loss and backpropagate the gradients to change the weights, to update the weights of the neural network, which will increase the performance of the neural network. So everything is supervised here. Discriminator is a binary classifier, class 1, class 0. It will try to learn. How? By adjusting its weights. This is also neural network. It is doing binary classification. Initially, it will also not do a great job. Slowly, it will improve to classify because it's a simple binary classification problem. It will learn. But more complex problem is to create the data. So generator needs to do a lot of hard work. So obviously, it will start with meaningless images, but slowly the weights will be updated in order to come up with better and better patterns, right? So yeah, neural network training, ma'am. So it is backpropagation, loss minimization, and updating the weights accordingly. So that is the reason it improves the performance.
Yes, sir. Yes, sir. Thank you, sir.
No problem. All right. So this is discriminator. What it tries to do is, if the data is real, P data means real. If X is coming from real, it will tries to give the probability 1. But if the data is fake, Z means coming from Z, that is why I say G of Z is the fake image. Output of G is the fake image that is being fed to discriminator. This, it has to be 0. The discriminated by the generator and has to assign a probability of 0. Here it is directly increasing the probability here, but it is 1 minus probability increasing. That means probability is decreasing. right? So this is how the loss is computed for discriminator. And basically generator has to fool the discriminator, right? Whatever discriminator does, it has to do the opposite. So the loss for generator is negative of the loss for discriminator. So it is seen as a fighting between two agents. One is the discriminator, another is the generator. Discriminator says you're wrong. Generator has to convince or fool the discriminator that he is right. So that way it is a game between these two players. It is called a mini-max player. One tries to minimize the probability, other tries to increase the probability, maximize the probability, right? Because the generator has to maximize the probability for the fake data, but the discriminator has to minimize because it has to identify that it is a fake, right? So this is a game. One fights to increase the probability, one fights to decrease the probability. That is called, it is called mini-max game. So in game theory also, a lot of people started looking at this generative adversarial neural network, and a lot of theory has been developed. I mean, I would say under development, not developed. It's only 6 years old. The concept itself is 6 years old, and it will take a lot of time because most of the things are not clearly understood. Although we have seen a lot of applications and a lot of empirical success is there. Empirical success means experimentally people have succeeded. I'll show some of the examples. So as I said, this is the um, deep convolutional GAN, where from the vector it tries to generate images. So let me show. So this is the discriminator side. It takes the input image and all the way it will come to one unit. It will predict the probability for real, right? This is a binary classification. You can think of any neural network classifier. All right. So these are some of the examples. These are examples generated by the data GAN. So look at these images. If you don't pay attention, if you just take a short look, they look like real images, bedroom images. So all these images are trained on, right? But if you actually pay attention, you will see a lot of discrepancy. They don't look like real, right? So, but they understood how a bedroom looks like, how a variety of bedrooms look like. They understood, right? That is the point here. Also, so they do a lot of interesting stuff also. So they take the Z for this image. This image has man with glasses, right? There is another Z that produces only man without the spectacles. So they took the difference between Z1 and Z2. So in a way, they extracted the representation for spectacles. And now that is being added to another Z which has produced a woman, right? So they have extracted the representation Z for the spectacles and added to this Z. Now they have seen women with specs, right? So these are very, very interesting vector space arithmetic where, one Z that has given a man's face with spectacles, and they have taken another Z that produced without the spectacles. So when they take the difference between these two, they somehow extracted the representation for the spectacles, and then that is being added to a woman's Z. So they have created, right? So this is how the model understands how to create different variety with different features, etc. Again, so this is where GAN is used in a supervised setup. There was one question whether we can use GAN in supervised or unsupervised. It can be used in both. In the top row, we are doing only unsupervised. There are data which belongs to 0, 1, 2, and so on, 9. All that we trained is to generate data. We don't care what class it belongs to, whether it is a 0, 1, 2, we don't care. It should look like a real digit. So that way, this is unlabeled. But if you see, this is called conditional GAN. You are generating with a condition. I want to generate a 5. So it generates a 5. I want to generate a 3. It will generate a 3. So you have trained the GAN by providing this label information also, right? So how do we do that? If we go here, now here, we can have a classifier instead of having real or fake, you can have um, another classifier with 0 to 9 classes also. And this training data also will have not only real, but 0, 1, 2, all the way 9. That label is also provided. So if you have the label information coming, the discriminator will tell that, and the generator will also try to learn that label. So that is called a conditional GAN framework, where you can train to generate a particular class. Yeah, as I said, GANs are not only generating images. Yeah, so these are all, I hope you can see the screen. This website also, I'll forward it to you. So these are all data provided by, sorry, generated by the GAN. Let me show, I'll play some of them because there is, yeah, so, okay, I'll play. So this is only a simple tune. So there are a lot of such experiments performed, and interestingly, it is making sense. That is the beauty of this research, right? They have trained the GANs to produce music. Based on the training music the GAN has seen, it is generates that genre, right? So it is also a creative task. Yeah, it has to be clearly understood what is happening inside, what the model is capturing, what it is training, all that. But it is clearly interesting and surprising because it is not making some meaningless noise. It is making a rhythmic output. So that is what is really interesting. That way, it is not only in the computer vision, but in the speech and NLP also. Yes, GANs create fake videos. This is also another very dangerous application, but I hope you see the.
The name is Hennessy. You know what I'm saying?
Yes, sir. Yes, sir.
The name is Hennessy, right? So everybody used to call me Bacardi. So I always call myself Bacardi, right? And then it was my Instagram name, like.
This is an actual, created video. You see the face of yeah, the face is clearly a male. He has a mustache, and the bird is also there, and the voice, lip sync, and the smoothness of this creation is if you don't know that this is actually a celebrity, we may even believe this as a real date.
For some reason, my Instagram keep getting deleted, and I think it was Bacardi that had something to do with it. So I just throw in there to Cardi B.
So this is a generated video. There are a lot of such videos. I might even show some of them. Really dangerous. Yes, ma'am. Please go ahead.
Sir, it's a couple of minutes to end the session, sir. Just I am intimating you.
Oh, okay, right. Yes, yeah. All right. I a couple of slides telling the.
Yeah, sir. You continue, sir. Just I am intimating that time is getting over.
No problem. Yeah. So these are all high quality generated images, as I shown in the beginning of the lecture. So you don't even believe that these are fake. We may think that these are some real people, but actually they are not. They are all created by the computer. So that's something really, really interesting. So image to image translation also. You just give only this much information, it will find out what makes meaningful, and it will add the color. For example, if you just give only this much, it will have the suitable color, which makes more sense. See, look at these things. The input is this one, and it is creating a realistic looking handbag image, right? So this is called image to image translation. A lot of such applications are there. Photos to emojis. So original photograph, it will create the emojis. So we are using a lot of these applications without actually knowing, right? In WhatsApp, you might have seen creating emojis from. So these are all in practice without actually we realizing them. And yeah, photo editing. So given this image, we want to change the hair color. If the woman is a blonde, how does it look like? If the woman smiles, how does it look like? If this woman becomes a male person, how does she look like? All those photo editing becomes very smooth with GANs. You change the parameters that are related to the smile coefficient, that are related to the random vector 1 to 1 cross 100. There are some components that are associated with the smiling aspect, all those things. You can manipulate them in order to result in different aspects. This also you have seen as a mobile app. Current photo is given, it will show you after 15-20 years how do you look like, right? This is face aging. If you are looking like this at 30, how would you have been at, right? So this person at 42 looks like this. How does he look like at 70? So this is all applications of GAN. We might have seen this already. I'm pretty sure some of you have done this. And this also super resolution. So we may have old time photos when the cameras are not very developed. We have only small resolution, right? So now using GANs, we can improve the quality of them. We can improve the resolution of those images. That is also a very good application. In painting is also another application where some of the data in the photograph is missing and the GAN will fill it meaningfully. Look at this dog. It doesn't look like a filled image. It looks like a very realistic. This also, the bird also, right? Wonderful applications. And I have shown only some of them. I'm pretty sure there are a lot of applications of GANs. So yeah, so this is what I had for today. Yeah, if you have some